All right, in this video, we're going to look at dimensional change, and this will be kind of my first video where we really lay the foundation. I want to give you a conceptual understanding of this process and why it is the way it is. And so first off, I want you to know what I mean when I say dimensional change. And so I'll just kind of read you our essential question. It's what happens to the surface area of a three-dimensional figure as we change the individual linear dimensions, and what happens to the volume. So in other words, if we were to take a figure and we were to like double the length, width, and height of it, how would that affect the surface area, that should say area, and how would it affect the volume? And here's a hint. It doesn't necessarily double like the linear dimensions do. So that's what I want you to keep in mind. If we take a figure and make every dimension on it twice as long, what happens to its surface area? What happens to its volume? And so first, I'd really like for you to write these things down because I want you to be fluent when we talk about units. We know that if I'm referring to linear units, we're talking about distances or lengths. And those are measured in linear units, inches, feet, or meters, and it's how long something is, okay? If you're measuring the height of an object or the length of an object, those are linear units. Next, if we're talking about square units, we're referring to areas like surface area. And this is our notation for it. We might say square inches, square feet, and square yards, because what you're doing is you're figuring out how many little squares it takes to cover something. So if we're talking about painting something, or wrapping something, like wrapping a gift, that's surface area. That's how much it takes to cover something, and it's measured in little squares, okay? And so lastly, if I'm referring to cubic units, that's when we're talking about volume, and that's when we're talking about filling something up. If I was saying how many little cubes fit in something, we refer to that as cubic inches, cubic feet, or cubic yards, because we're saying how many little cubes it takes to fill something up. So while this is wrapping or painting, this would be filling something up. So be familiar with these different types of units. And so here's what we're going to look at first. We're going to look at surface area, and we're going to figure out what happens to the surface area if we double or triple the side lengths of a figure. And we're going to start with a cube. We're going to use a cube because I think it makes it easiest to visualize these relationships. Note that these relationships would be true if I had a rectangular prism, triangular prism, cones, all sorts of these things. But first, let's start by establishing the surface area of this figure. And so each face has an area of 1 square unit, because if this has a length of 1, and this has a height of 1, and then we've got a width of 1, that means we have these congruent squares on every face, and every single face is a 1 by 1 square. So this has an area of 1, this has an area of 1, this has an area of 1, and then there's 3 more faces that we can't see from here. So our surface area of the original cube is 6 square units. Now, let's say I were to dilate this by a scale factor of 2. Every dimension, the length, the width, and the height were all multiplied by 2. We would create a cube that looks like this. So what I want you to think about is as we doubled each side dimension, did the surface area double? In other words, is the amount of paint used to paint this, is it twice as much as the amount of paint we would use here? Well, now that we're looking at it, we see that each one of the individual faces now has an area of 4, because the area of this face would be created by doing 2 times 2. So if this face has an area of 4 square units, and there's 6 faces in the whole figure, then the entire figure has an area, or a surface area, of 24 square units. And you might notice that, okay, we doubled the side lengths, but the surface area did not necessarily double. We're going to come back and examine what's actually happening to that surface area in a minute. But first, let's look at what happens if we triple. So let's come back. We come back to our original figure. And let's say we multiplied it by a scale factor of 3. So now the length, width, and height are now 3, 3, and 3. Well, here now we've created 6 faces, and each face is congruent. But this face has an area of 9 square units now, because 3 times 3 would give me 9 units here, 9 square units on this face, 9 square units on this face, 9 square units on the top, and then the 3 faces we can't see on the back would also have an area of 9. So we have 6 faces with an area of 9 square units, and so our surface area is going to be 54 square units. Now, what we want to do now is we want to see the pattern. As I doubled the side lengths, what happened to the surface area? As I tripled the side lengths, what happened to the surface area? And as I look at this, what I want us to recognize, oh, I kind of gave it away right there, is that whenever I multiply the side lengths by 2, and by 2, our area, our surface area, is in square units. So that doubling affects it twice. If I multiply by 2 and multiply by 2, this surface area is going to increase by a factor of 2 squared, 2 times 2, okay? So as we double the side lengths, the surface area increases by 2 squared. As we tripled the side lengths, the surface area increased by 3 squared because tripling it affected the length. For example, for this face, I should say, it affected the width and the height. So that times 3 affected it not once but twice in the calculating of these individual areas. So here's what I want you to write down and remember. This is kind of our main idea, is that the relationship between the scale factor and surface area is that when the scale factor is x, in other words, whenever we double it or multiply by x, that the surface area increases by the square of that scale factor. Note that as we doubled or did times 2 for our side lengths, the surface area did times 2 squared. If we tripled our side lengths, then the surface area increased by times 3 squared. Okay? Now, that's what happens with our surface areas. Let's investigate what happens with our volumes. Okay? So let's start with this figure. This figure, if we were to find the volume of it, this is a unit cube. And so 1 times 1 times 1 would give you the volume, the area of the base times the height. And this would have a volume of 1 cubic unit. In other words, it's one little cube, right? And so, what would happen if we doubled it? Well, now we have 2 times 2 times 2 to find the volume. And you can actually just see by visualizing it, if there's 1 cube here, there's 8 cubes here. So the volume of our cube, when we double the side lengths or use a scale factor of 2, our volume did not double. Now let's look at tripling, or using a scale factor of 3. Well, if you multiply by 3 times 3 times 3, you can maybe guess what the volume is here, but we also can just recognize by counting the cubes. I see on this base layer there's going to be 9 cubes. On the second layer there's going to be 9 cubes. And on this third layer, there's going to be 9 cubes. So we can just see that there's going to be 27 little cubes in there. In other words, its volume is 27 units cubed. Forgive my typo right there. These should all say cubic units. So please pretend that's a little 3, that's a little 3, and that's a little 3. Okay? Now, as we're looking at this, what happens whenever we do the scale factor by a certain number? Since we're dealing in cubic units, that scale factor comes into play 3 times. It came into play on the length, the width, and the height. That's why, as our scale factor may use a factor of x, the volume would increase by a factor of x to the 3rd power. Because that scale factor is going to affect the length, width, and height of our figure. Okay? In other words, if we doubled the side lengths, the volumes would increase by 2 to the 3rd power, your scale factor cubed. As we triple the side lengths, then our volume increases by the scale factor cubed. If we quadrupled the side lengths, then our volume would increase by 4 to the 3rd. But this is what I want us to know. While for surface areas it increased by a factor of x squared, for volumes it's going to increase by a factor of x cubed. Now, we're just going to do one short little practice problem. Maybe we're not. We are not, because I didn't include it on this slide. So we are going to stop there for now. And I really just want you to remember and write down this relationship. This is the basic idea of what you need to know. And in our next video, we're actually going to do some practice problems.